Hello friends, in this session we discuss series with alternatively positive and negative terms and discuss their convergence. Like any series, an alternating series converges if and only if the associated sequence of partial sums converges. We know that a series with all its terms non-negative either converges or diverges, but never oscillate. But an alternating series either converges or oscillates. Leibniz test for verifying the convergence of alternating series will be discussed. We also discuss the notion of absolute convergence and conditional convergence of series. Alternating series. A series in which the terms are alternatively positive and negative is an alternating series. The following are examples of alternating series. 1 minus 1 upon 2 plus 1 upon 4 minus 1 upon 8 plus etc. plus negative 1 power n plus 1 1 upon 2 power n plus 1 plus etc. Negative 1 plus 2 minus 3 plus 4 minus etc. plus minus 1 power n into n plus etc. The alternating series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc. plus minus 1 power n plus 1 upon n plus etc. is called the alternating harmonic series. Notation: an alternating series may be written as summation negative 1 power n plus 1 into a n where n from 1 to infinity, where each a n is positive and the first term is positive. If the first term in the series is negative, then we write the alternating series as summation negative 1 power n a n where n from 1 to infinity. Let us consider an example where a necessity to deal with an alternating sum arises in a natural way. Imagine an object is moving back and forth along a one-dimensional line. The object moves 1 meter to the right and 1 meter to the left in a repeated cycle indefinitely. We calculate the displacement of the object relative to the standing point when the object was first set in motion. So, after one movement to the right, the object's displacement is S1 equal to 1. Then after one move to the right and one move to the left, the object's displacement is S2 equal to 1 minus 1 equal to 0. In general, we conclude that S2n minus 1 equal to 1 and S2n equal to 0 for n equal to 1, 2, 3 etc. That is, after an odd number of movements, the object is at 1 meter from the starting point, and after an even number of movements, it is back at its starting point. This is an example of an object that never settles into any particular spot along the one-dimensional line. Instead, it keeps bouncing back and forth from x equal to 0 and x equal to 1 along the one-dimensional axis. To force the object to slow down and to stay at a particular location, we must change the magnitude of the move to the right and move to the left. Obviously, we do not want to make the magnitudes larger than they were initially. Instead, for example, let us suppose the first movement is 1 meter, the second move is half meter and third is 1 upon 3 meters. The fourth is 1 upon 4 meters and so on. We can write the displacement of the object as a sum. After n moves, the object's position is Sn equal to summation negative 1 power n upon n where n from 1 to n. The question of eventually settling into a location is related to the convergence of its sequence. If the sequence of partial sum of the series summation negative 1 power n upon n where n from 1 to infinity converges, then the object will slow down and settle into some fixed point. We will answer the question of whether this series converges with the help of Leibniz test or alternating series test. Theorem 1, Leibniz test or alternating series test. An alternating series of either form summation negative 1 power n plus 1 un where n from 1 to infinity or form summation negative 1 power n un where n from 1 to infinity converges if the following two conditions are satisfied. First one, u1 greater than or equal to u2 greater than or equal to etc. greater than or equal to uk greater than or equal to uk plus 1 etc. And second one, limit of un as n approaches infinity is 0. That is, the given alternating series converges if the terms are non-increasing and tends to 0 as n tends to infinity. Attention, a common mistake is to try to apply the conditions of the Leibniz test and then upon discovering that some condition does not hold, conclude that the series diverges. The theorem only says that if the conditions are true, then the series converges. It does not say that what happens if the conditions are not true. On the other hand, if limit of un as n approaches infinity not equal to 0, we can conclude that the series diverges by the nth term test of divergence of series. Also, unlike the integral test and the comparison test, Leibniz test will only tells us when a series converges and not if a series will diverge. Another point to note is that we need only require that the terms of the series eventually decreases. We may very well have a first few terms of the series may not have decreasing behavior. This is possible as addition or deletion of finitely many terms of a series never hurts its convergence or divergence behavior. With this in mind, the theorem on Leibniz test can be stated as follows. An alternating series of either form summation negative 1 power n plus 1 un where n from 1 to infinity or form summation negative 1 power n un where n from 1 to infinity converges if the following two conditions are satisfied. First one, there exists a natural number k such that uk greater than or equal to uk plus 1 greater than or equal to uk plus 2 greater than or equal to etc. And second one, limit un as n approaches infinity is 0. We now prove the theorem. We first recall monotone convergence theorem. A monotone sequence of real numbers is convergent if and only if it is bounded. Now we prove the present theorem. Let Sn equal to u1 minus u2 plus u3 minus u4 plus etc. plus minus 1 power n minus 1 un. Now for all n, S2n plus 2 minus S2n equal to u2n plus 1 minus u2n plus 2 greater than or equal to 0 implies S2n plus 2 greater than or equal to S2n implies sequence S2n is a monotonic increasing sequence. Again, S2n equal to u1 minus u2 plus u3 minus etc. plus u2n minus 1 minus u2n, which is equal to u1 minus u2 minus u3 minus u4 minus u5 minus etc. minus u2n minus 2 minus u2n minus 1 minus u2n. But since un plus 1 less than or equal to un for all n, therefore each bracket on the right is positive and hence S2n less than u1 for all n. Thus, the monotonic increasing sequence S2n bounded above and hence by monotone convergence theorem sequence S2n is convergent. Let limit S2n as n approaches infinity is S. We shall now show that the sequence S2n plus 1 also converges to the same limit S. Now, S2n plus 1 equal to S2n plus u2n plus 1. Therefore, limit of S2n plus 1 as n approaches infinity is limit of S2n as n approaches infinity plus limit of u2n plus 1 as n approaches infinity. But by the condition 2, limit of u2n plus 1 as n approaches infinity is 0. Therefore, limit of S2n plus 1 as n approaches infinity equal to limit of S2n as n approaches infinity plus 0, which is equal to S plus 0, which is equal to S. Thus, the sequence Sn and the sequence S2n plus 1 both converges to the same limit S. We shall now show that the sequence Sn also converges to S. Let epsilon greater than 0 be given. Since the sequence S2n and S2n plus 1 both converges to S, Therefore, there exist positive integers m1, m2 respectively such that absolute value of S2n minus s less than epsilon for all n greater than or equal to m1, equation number 1, and absolute value of S2n plus 1 minus s less than epsilon for all n greater than or equal to m2, equation number 2. Thus, from equation 1 and 2, we have absolute value of Sn minus s less than epsilon for all n greater than or equal to maximum of 2m1, 2m2 plus 1. Implies sequence Sn converges to S. Implies the series summation negative 1 power n minus 1 un converges. We examine the convergence of the series 1 upon 1 power p minus 1 upon 2 power p plus 1 upon 3 power p minus 1 upon 4 power p plus etc. where p greater than 0, writing the series in the form summation negative 1 power n plus 1 an where n from 1 to infinity. We have an equal to 1 upon n power p and an plus 1 upon an equal to n power p upon n plus 1 whole power p, which is equal to 1 upon 1 plus 1 upon n whole power p, which is strictly less than 1 since p greater than 0. Thus, an plus 1 strictly less than an. Also, since p greater than 0, limit of an as n approaches infinity equal to limit of 1 upon n power p as n approaches infinity is 0. Hence, all the conditions of Leibniz test are satisfied and hence the given series converges. Particular cases. First one, with p equal to 1, the alternating harmonic series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc. plus negative 1 power n plus 1 upon n plus etc. is convergent. Second one, with the p equal to 1 upon 2, the series 1 minus 1 upon square root of 2 plus 1 upon square root of 4 minus 1 upon square root of 8 plus 1 upon square root of 16 plus etc. is convergent. Third one, with the p equal to 5 upon 2, the series 1 minus 1 upon 2 square root of 2 plus 1 upon 3 square root of 3 minus 1 upon 4 square root of 4 plus etc. converges. We test the convergence of 1 upon x minus 1 upon x plus a plus 1 upon x plus 2a minus 1 upon x plus 3a plus etc. x and a being positive quantities. The given series is an alternating series with the un equal to 1 upon x plus n minus 1 times a. Since a greater than 0, we have x greater than x plus a greater than x plus 2a greater than x plus 3a greater than etc. Equation number 1. As all the terms in equation 1 are positive, recalling that if a greater than 0 and b greater than 0, with a greater than b, then 1 upon a less than 1 upon b. We have 1 upon x less than 1 upon x plus a less than 1 upon x plus 2a less than 1 upon x plus 3a etc. Hence, the terms of the series are in the decreasing order. Also, limit of un as n approaches infinity equal to limit of 1 upon x plus n minus 1 times a as n approaches infinity, which is equal to 1 upon limit of x plus n minus 1 times a as n approaches infinity, which is equal to 0. Hence, for the given alternating series, all the conditions of Leibniz test are satisfied and also it is convergent. We test the convergence of summation negative 1 power n upon logarithm of n where n from 2 to infinity. The given series is an alternating series. Also, u2 equal to 1 upon logarithm 2, u3 equal to 1 upon logarithm 3, u4 equal to 1 upon logarithm 4 with u2 greater than, u3 greater than, u4 greater than, u5 greater than etc. In general, un equal to 1 upon logarithm n with un greater than un plus 1. Also, limit of un as n approaches infinity is limit of 1 upon logarithm n as n approaches infinity, which is equal to 1 upon limit of logarithm n as n approaches infinity, which is equal to 0. Hence, all the conditions of Leibniz test are satisfied by the given alternating series and so it is convergent. Let us examine the convergence of the series x upon 1 plus x minus x square upon 1 plus x square plus x cube upon 1 plus x cube minus etc. 0 less than x less than 1. With the un equal to x power n upon 1 plus x power n and un plus 1 equal to x power n plus 1 upon 1 plus x power n plus 1. We have un minus un plus 1 equal to x power n upon 1 plus x power n minus x power n plus 1 upon 1 plus x power n plus 1, which is equal to x power n into 1 upon 1 plus x power n minus x upon 1 plus x power n plus 1, which is equal to x power n into 1 minus x upon 1 plus x power n into 1 plus x power n plus 1. Since x is positive and less than 1, un minus un plus 1 greater than 0. Hence, un plus 1 less than un for all n. Also, limit to un equal to limit of x power n upon 1 plus x power n, which is equal to 0. Since with the 0 less than x less than 1, x power n converges to 0 as n approaches infinity. Hence, all the conditions of Leibniz test are satisfied and the series is convergent. Absolute and conditional convergence of series. We have discussed various convergence tests which we can be used to test the convergence of series of non-negative terms or of alternating series. Now, we consider series with arbitrarily positive or negative terms. We begin with a definition. A series summation un n from 1 to infinity equal to u1 plus u2 plus u3 plus etc. plus un plus etc. where un may be positive or negative is said to be absolutely convergent if the series of absolute value summation absolute un where n from 1 to infinity equal to absolute value of u1 plus absolute value of u2 plus absolute value of u3 plus etc. plus absolute value of un plus etc. converges. If the series summation absolute value of un n from 1 to infinity diverges, then the series summation un n from 1 to infinity is said to diverge absolutely. We see that the series 1 minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus 1 upon 5 square minus etc. is absolutely convergent. Since the series 1 plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square plus 1 upon 5 square plus etc. being the hyperharmonic series summation 1 upon n power p n from 1 to infinity with p equal to 2 is convergent. The alternating harmonic series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc. does not converge absolutely as the corresponding series of absolute value in the divergent harmonic series 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus etc. Now, consider this example. By Leibniz test, the series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc. is convergent. But the series formed by the absolute value of the terms is summation absolute value un equal to 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus etc. which is equal to summation 1 upon n. The harmonic series which is divergent. In such cases, we say that series is conditionally convergent. Hence, the series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc. is conditionally convergent. More precisely, we have the following definition. If summation absolute value of un where n from 1 to infinity is divergent, but summation un where n from 1 to infinity is convergent, then summation un n from 1 to infinity is said to be conditionally convergent. Theorem 2, the absolute convergence test. An absolutely convergent series is necessarily convergent. That is, if summation absolute value of un where n from 1 to infinity converges, then summation un where n from 1 to infinity converges. Attention, the converse of the above theorem is not true. For example, the series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5 minus etc. converges, but the corresponding absolute series 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus 1 upon 5 plus etc. is divergent. We test whether the series 1 plus 1 upon 2 square minus 1 upon 3 square minus 1 upon 4 square plus 1 upon 5 square plus 1 upon 6 square minus 1 upon 7 square minus 1 upon 8 square plus etc. is absolutely convergent or not. Does the series converge? The series of absolute term is 1 plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square plus 1 upon 5 square plus 1 upon 6 square plus 1 upon 7 square plus 1 upon 8 square plus etc., which being a hyperharmonic series with p equal to 2 strictly greater than 1, which is convergent. Hence, the given series is absolutely convergent, and hence in view of the theorem the given series is convergent. Alternating p series. Using Leibniz test, we have seen that the alternating p series summation negative 1 power n plus 1 upon n power p, where n is from 1 to infinity, p greater than 0, converges. Now, the series formed by the absolute values of the terms is the hyperharmonic series summation 1 upon n power p, n is from 1 to infinity, and it converges for p greater than 1 and diverges for p less than or equal to 1. Hence, the given alternating p series converges absolutely if p greater than 1 and converges conditionally if 0 less than p less than or equal to 1. In particular, 1 minus 1 upon square root of 2 plus 1 upon square root of 3 minus 1 upon square root of 4 plus etc. is conditionally convergent series, while 1 minus 1 upon 2 power 3 upon 2 plus 1 upon 3 power 3 upon 2 minus 1 upon 4 power 3 upon 2 plus etc. is an absolutely convergent series. Theorem 3, ratio test for absolute convergence. Let summation un n from 1 to infinity be a series with non-zero terms, and suppose that rho equal to limit of absolute value of un plus 1 upon absolute value of un as n approaches positive infinity. First one, if rho less than 1, then the series summation un n from 1 to infinity converges absolutely and therefore converges. Second one, if p greater than 1 or if p equal to positive infinity, then the series summation un n from 1 to infinity diverges. Third one, if p equal to 1, no conclusion about convergence or absolute convergence can be drawn from the test. Examine the convergence or divergence of the series summation negative 1 power n 2n minus 1 factorial upon 3 power n, where n from 1 to infinity. The absolute value of the general term un is given by absolute value of un equal to absolute value of negative 1 power n into 2n minus 1 factorial upon 3 power n, which is equal to 2n minus 1 factorial upon 3 power n. Thus, rho equal to limit of absolute value of un plus 1 upon absolute value of un as n approaches infinity, which is equal to limit of 1 upon 3 into 2n plus 1 factorial upon 2n minus 1 factorial as n approaches infinity, which is equal to 1 upon 3 into limit of 2n into 2n plus 1 as n approaches infinity, which is equal to infinity. Hence, by ratio test for absolute convergence, the given series diverges. Grouping of series. Given a series summation xn, we can construct many other series summation yk by leaving the order of the terms xn fixed, but inserting parentheses that group together finite numbers of terms. For example, the series indicated by 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5 minus 1 upon 6 plus 1 upon 7 minus 1 upon 8 plus 1 upon 9 minus etc. plus 1 upon 13 minus etc. is obtained by grouping the terms in the alternating harmonic series. It is an interesting fact that such grouping does not affect the convergence or the value of convergent series. Theorem 4. If a series summation xn is convergent, then any series obtained from it by grouping the terms is also convergent and to the same value. Attention, the converse of the above theorem is not true. For example, the grouping 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus etc. produces a convergent series that converges to 0 from the divergent series summation negative 1 power n, n from 0 to infinity diverges since the terms do not approach 0, the nth term test of divergence. Rearrangement of series. Definition: a series summation yk in R is a rearrangement of a series summation xn if there is a bijection f of n, the set of natural numbers onto n, such that yk equal to x of fk for all k belongs to n. Illustration: two rearrangements of the alternating harmonic series 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5 minus 1 upon 6 plus etc. equation 1 are 1 minus 1 upon 2 minus 1 upon 4 plus 1 upon 3 minus 1 upon 6 minus 1 upon 8 plus 1 upon 5 minus 1 upon 10 minus 1 upon 12 plus etc. equation number 2, in which each positive term is followed by two negative terms, and 1 upon 2 plus 1 upon 4 plus 1 upon 6 plus etc. plus 1 upon 2 power 8 minus 1 plus 1 upon 2 power 8 plus 2 plus etc. plus 1 upon 2 power 16 minus 1 upon 3 plus etc. equation number 3. Rearrangement may affect convergence. We have seen earlier that grouping series does not affect the convergence of a series, but making rearrangement of a series may affect convergence. Theorem 5, Riemann's theorem. The term of any conditionally convergent series can be rearranged to give either a conditionally convergent series having as arbitrarily pre-assigned number, or a divergent series or an oscillatory series. Corollary: if summation xn is a conditionally convergent series in R, and if C belongs to R is arbitrary, then there is a rearrangement of summation xn that converges to C. We illustrate the corollary to Riemann's theorem by an example. We can find a rearrangement of summation negative 1 power n plus 1 upon n, where n from 1 to infinity, that will converge to any pre-assigned real number, say for example 809. We know that 1 plus 1 upon 3 plus 1 upon 5 plus etc. diverges, and hence the partial sum of the series must be unbounded. Hence, it is possible to find a positive odd integer m greater than 0 such that 1 plus 1 upon 3 plus 1 upon 5 plus etc. plus 1 upon m strictly greater than 809. Let m1 be the smallest odd integer such that 1 plus 1 upon 3 plus 1 upon 5 plus etc. plus 1 upon m1 greater than 809. Then 1 plus 1 upon 3 plus 1 upon 5 plus etc. plus 1 upon m1 minus 1 upon 2 less than or equal to 809. Now let m2 be the smallest odd integer greater than m1 such that 1 plus 1 upon 3 plus 1 upon 5 plus etc. plus 1 upon m1 minus 1 upon 2 plus 1 upon m1 plus 2 plus etc. plus 1 upon m2 greater than 809. Then 1 plus 1 upon 3 plus 1 upon 5 plus etc. plus 1 upon m1 minus 1 upon 2 plus 1 upon m1 plus 2 plus etc. plus 1 upon m2 minus 1 upon 4 less than or equal to 809. Continuing in this manner, it is possible to construct a rearrangement of summation negative 1 power n plus 1 upon n, where n from 1 to infinity, that converges to 809. The method used in the above example is this. Firstly, observe that the given conditionally convergent series has infinitely many positive terms and infinitely many negative terms, and that both the series of positive terms and the series of negative terms diverge. To construct a series converging to C, we take positive terms until the partial sum is greater than C, then we take negative terms until the partial sum is less than C, then we take the positive terms until the partial sum is greater than C, then we take the negative terms, etc. Theorem 6, rearrangement theorem or Dirichlet's theorem. Let summation xn be an absolutely convergent series in R. Then any rearrangement summation yn of summation xn converges to the same value. Remarks. First one, for a series of positive terms, the theorem may be stated as follows. A series of positive terms, if convergent, has a sum independent of the order of its terms, but if divergent, it remains divergent, however its terms are rearranged. Second one, Dirichlet's theorem shows that the brackets may be inserted or removed or terms be picked at, placed at random without changing the behavior of a positive term series or an absolutely convergent series. In fact, they behave exactly like finite sum. Third one, an absolutely convergent series, because it remains convergent with unaltered sum under every rearrangement of terms, is also called unconditionally convergent. Let us summarize the session. In this session, we have discussed series with alternatively positive and negative terms and discussed their convergence. Leibniz test for verifying the convergence of alternating series have been discussed and illustrated through examples. Absolute convergence and conditional convergence of series also have been discussed. We observe that if a series is convergent, then any series obtained from it by grouping the terms is also convergent and to the same value. We have seen that the terms of any conditionally convergent series can be rearranged to give either a conditionally convergent series having as a some arbitrary pre-assigned number or a divergent series or an oscillatory series. Hope you all enjoy the session. See you next time. Until then, goodbye.